What are Gödel's incompleteness theorems? How have some thinkers used them to argue that artificial intelligence can never truly think or understand? And most importantly, do those arguments actually succeed? Hello everyone, I'm Michael Augros, a philosopher by trade and a longtime member of the teaching faculty at Thomas Aquinas College. Welcome to the 7th installment in this 10-part series exploring whether artificial intelligence can genuinely think and understand. In our last video, we examined some arguments for the conclusion that AI lacks intelligence in the primary literal sense in which we human beings possess it. In this video, we'll explore a couple more. Why devote a whole video to just 2 AI arguments? Mainly because these two take more time and effort to grasp. That's because truly comprehending those arguments requires us to understand certain theorems due to Gödel, which takes some time if we're starting from scratch. But that effort is worthwhile, first because Gödel's theorems are fascinating in themselves, and second because the AI arguments based on them are taken by some very sharp minds to be completely decisive. As we'll see, there's reason to question that confidence, but if these arguments really do settle the issue, that's obviously worth knowing. And even if they fall short of that, well, that's important to know too. Both arguments we'll examine are rooted in the famous incompleteness theorems of Kurt Gödel. Gödel was an Austrian-born, German-speaking logician, mathematician, and philosopher who emigrated to the United States in 1940, thus avoiding conscription into the German army during World War II. He published his 2 incompleteness theorems in 1931. One of the AI arguments we'll examine is based on the first theorem and the other on the second. To help guide you through the discussion, I've structured the video in 6 parts. Part 1 lays out the prerequisites for understanding Gödel's incompleteness theorems. Part 2 gives a clear statement of both theorems and presents overviews of Gödel's proofs for them. Part 3 constructs the 2 AI-related arguments based on those theorems. Parts 4 and 5 respectively consider criticisms of the AI arguments based on Gödel's first and second theorems. And in Part 6, I'll offer my own overall assessment of the 2 AI arguments. One last introductory note before we jump into Part 1. This is one of the longer videos. As I said, that's because it not only describes and evaluates the AI arguments based on Gödel's theorems, but also, as preparation, provides a fairly comprehensive overview of those 2 theorems themselves. It seemed to me that without offering that, I'd be leaving anyone unfamiliar with those theorems, yet willing to learn about them, unable to follow the subsequent AI arguments and their evaluations in the most satisfactory way. And Gödel's theorems are pretty intense pieces of mathematical logic, hence the length of this video. Also, just as in video 2, I need to say something to 2 potential types of viewers, experts and non-experts. If you happen to know Gödel's theorems like the back of your hand, you may want to skip ahead to the part of this video where we jump into the AI arguments based on them. And if you mathematicians and logicians choose to watch my attempt to explain the theorems to a general audience, I ask your patience. I will be less precise than you would be. On the other hand, if you've never heard of Gödel's theorems and you find my explanations too fast to follow completely and retain, don't worry. Just let the discussion make whatever impression it makes on you, and I think you'll find you've picked up enough to follow the subsequent AI arguments with ease. If you want to jump straight to the AI arguments without hearing about Gödel's theorems, either because you're already familiar with his work or because you don't want to invest time in it, you can skip to about the last quarter of this video. That's where I discuss those arguments. Let's begin Part 1. The prerequisites for understanding what Gödel's 2 theorems actually state. To get a solid grasp of them, we'll briefly cover 5 foundational ideas. First, the concept of a formal system. Second, some important notions of consistency. Third, the concepts of decidability and completeness. Fourth, the special mapping technique known as arithmetization. And fifth, the idea of a system being sufficiently rich for Gödel's theorems to apply to it. Let's start with the idea of a formal system. One way to get into this is to look at what originally motivated logicians to develop such systems in the first place. So here's a very quick look at one of the major early motivations. In the 19th century, non-Euclidean spaces began to emerge as serious objects of study. mathematicians came to accept that Euclidean space wasn't the only conceivable kind of space. Other kinds were possible too, such as hyperbolic space, elliptic space, spherical space, and so on. Hyperbolic space, for example, is infinite and unbounded like Euclidean space, but it differs in several key ways. For instance, parallel lines tilt toward one another, though they never intersect. There are no rectangles, and if two triangles have the same shape, they must also be the same size. Every triangle in hyperbolic space has an angle sum of less than 180 degrees. It's a pretty strange geometry, but we arrive at it by keeping Euclid's first four postulates and denying the applicability of his fifth postulate to the lines called straight in such a space. Originally, mathematicians tried to prove that hyperbolic space was logically impossible, hoping to show that only Euclidean geometry was free of contradiction. But they failed. Despite centuries of effort to prove Euclid's fifth postulate from his first four postulates, which would effectively prove that hyperbolic geometry is self-contradictory, no one could find any such proof of that postulate, nor could anyone find a contradiction in hyperbolic geometry. Of course, not finding a contradiction isn't the same as proving that no contradiction exists. There was still the possibility that some subtle inconsistency had simply gone undetected. So the question remained, was hyperbolic geometry really self-consistent? Or at least, could it be shown to be as consistent as Euclidean geometry? That might sound impossible to determine without examining every possible argument in both geometries, which is clearly unmanageable. But mathematicians found another way. Eugenio Beltrami, Felix Klein, Henri Poincaré, and others discovered that certain structures within Euclidean geometry behaved in exactly the same way as the structures in hyperbolic geometry. For example, in Poincaré's disk model, hyperbolic geometry is represented inside a single Euclidean circle, where arcs of circles drawn orthogonally to the boundary mimic hyperbolic straight lines. When these arcs intersect at certain angles, they behave just like hyperbolic lines intersecting at those same angles. And the logarithmic lengths of the arcs correspond to the actual lengths of the hyperbolic lines. We don't need the technical details here. What matters is this. Such correspondences let mathematicians build a kind of dictionary that translates between Euclidean disk geometry and hyperbolic geometry. Any true statement in one could be converted into a true statement in the other by systematically replacing terms. This kind of one-to-one correspondence is called a mapping. Each object in hyperbolic space maps to a corresponding object in Euclidean space that behaves the same way logically. Thanks to this perfect mapping, any valid proof in hyperbolic geometry has a corresponding proof in the Euclidean disk model. And that means if hyperbolic geometry ever produced a contradiction, if it ever proved both a statement and its negation, then by the mapping, Euclidean geometry would also prove a contradiction. In other words, hyperbolic geometry can't be any less self-consistent than Euclidean geometry is. Much more could be said about that. And of course, that quick overview won't give a full picture to someone unfamiliar with the topic, but that's fine. What we really want to draw out is how this kind of mapping between one system of thought and another, where corresponding elements behave the same way, motivates the idea of a formal system. To construct such a mapping, we need to isolate the logic that's present in the statements and arguments of one geometry and show that it also appears in another. All of us do something similar when we evaluate arguments about other subjects besides geometry. If someone makes a dubious argument, we often refute it by showing that the same logic would lead to an obviously bad conclusion in a different context. Take this argument. Every cat is a mammal. No bird is a cat. Therefore, no bird is a mammal. The conclusion happens to be true, but the argument is no good. To show that this argument isn't valid, we can extract its logical form, its structure, and present it independently of the specific terms. The first premise, for instance, has a subject, cat, a predicate, mammal, and a universal quantifier, every, all linked by the copula is. To capture that logical structure in abstract form, we use symbols. Every A is a B. If we do that for all three statements, we get every A is a B, no C is an A, therefore no C is a B. Now, if this form were logically valid, then substituting any terms for A, B, and C in a way that gave us true premises should also yield a true conclusion. But suppose we let A be cat, B be animal, and C be dog. Then we get every cat is a mammal, no dog is a cat, therefore no dog is a mammal. The premises are still true, but the would-be conclusion is false, so the form is invalid. And since our original argument has the same form, it's invalid as well. Now, what if we want to do this kind of thing not just with one argument, but with all the arguments in a whole system of thought, say Euclidean geometry, and compare them with all the arguments in another system, like hyperbolic geometry? Eventually, even writing out words like every gets tedious. So we start replacing those with symbols as well. And if we want to prove that a system's axioms can't derive a particular statement, we may need many layers of reasoning in our logically abstract language. To make that easier, we adopt conventions that streamline the process, transforming it into something more like algebra than essay writing. That's why mathematical logicians end up formalizing a statement like, every cat is a mammal, this way. Here, Cx means x is a cat, Mx means x is a mammal, and the upside-down a is a universal quantifier meaning for all x. So the expression as a whole reads, for all x, if x is a cat, then x is a mammal. Now that isn't exactly the same as the English sentence, every cat is a mammal, but it's logically equivalent for most formal purposes. What matters is that it captures the logical structure without the ambiguities, specificities, or lengthiness of ordinary language. That's what we mean when we say a statement is formalized. Its logical pattern has been extracted from the specific context. With that, we can now define a formal system. A formal system is a well-defined framework for deriving theorems from axioms using a fixed set of rules. If you take any deductive body of thought, like Euclid's geometry, number theory, or Einstein's relativity, and formalize its terms and postulates, you get a formal system. That system will include 4 components: primitive symbols, syntax, axioms, and rules of inference. Primitive symbols are the basic symbols or alphabet of the system. Each one stands for something, whether a concept, a variable, or a logical operator, but they're not used to form words, since words have been replaced with symbols in this scheme. Syntax is the system's grammar, the rules that determine how symbols can be combined to form well-formed, that is, correctly formed, formulas. Axioms are foundational statements, written in the system's symbols and syntax, and they're taken as given. These serve as the starting points for deriving theorems. Rules of inference are the logical rules that tell us what new statements we're allowed to derive from existing ones. And that's it. If you have a set of primitive symbols, a syntax, a collection of axioms, and some rules of inference, then you have a formal system. Next on the list of prerequisites for understanding Gödel's incompleteness theorems is the idea of consistency. At its core, this means that 2 or more statements are in agreement. They don't contradict each other. We'll distinguish 3 kinds of consistency. The first kind is the most intuitive and familiar. In this primary, ordinary, and strictest sense, 2 or more statements are consistent if they don't directly contradict each other and if no contradiction can be derived from them by any sound reasoning, no matter what additional true statements we use, including true statements that cannot be expressed within the system itself. The opposite, of course, is inconsistency, where 2 or more statements either directly contradict or allow contradictions to be logically derived when combined with certain true premises. For example, some apples are red and some apples are green are consistent with each other, and both are also consistent with some apples are not red. But some apples are red and no apples are red are inconsistent. They directly contradict. Likewise, x is an even number, x is greater than 2, and x is prime are jointly inconsistent, not because any 2 directly contradict, but because the first 2 statements imply that x is not prime, which contradicts the third. Socrates was famous for exposing inconsistencies, so we can use him to illustrate the concept. For instance, if his friend Meno says both P and Q, where P and Q are statements, and if it follows logically from P and some true statement T, even one that Meno doesn't admit, that not Q is the case, then he's being inconsistent in this first sense. That captures the most common sense of consistency. But there's a second, more technical and weaker sense that applies specifically to formal systems. A formal system F is consistent in this weaker sense if no contradiction can be derived within the system. That is, no 2 axioms contradict each other and no 2 provable statements within F contradict each other. So Meno would be inconsistent in this weaker sense only if what he himself has admitted leads by sound reasoning to a contradiction. If he doesn't admit T, even if T is true, then he may still be consistent in this weaker internal sense. There's also a third sense of consistency, which is a somewhat stronger sense of internal consistency, and which Gödel called omega consistency. This is best understood by first looking at its opposite, omega inconsistency. Here's an informal way to think about it. Suppose we have a formal system F that talks about natural numbers. Imagine that system F proves the general statement there exists a natural number with property P, but at the same time system F proves the particular statements 0 does not have property P, 1 does not have property P, 2 does not have property P, 3 does not have property P, and so on for every specific natural number. Well, that's clearly a problem. On the one hand, the system says in a general way that some natural number has property P, but on the other hand, if you pick any particular natural number, the system denies that property P belongs to it. That's a contradiction, but not an outright one, either in the ordinary or the internal sense. The contradiction only becomes obvious when you step outside the system and interpret what its theorems are really saying. In such a case, we say the system is omega inconsistent. It doesn't directly contradict itself within its own rules, but it still manages to say something self-undermining about natural numbers. By contrast, a system is omega consistent if this kind of thing never happens, if it never proves the general statement that some number has property P while also denying P of every individual number. Now, important point. If a system is inconsistent in the earlier ordinary sense, meaning it outright contradicts itself, then it's also omega inconsistent. But the reverse is not true. A system can be omega inconsistent without ever producing any direct within-the-system contradiction. For example, it might prove there exists a number with property P without being able to prove which number has it. It also proved that 0 doesn't have P, 1 doesn't have P, 2 doesn't have P, and so on, as we said. That kind of contradiction flies under the radar unless you look at the pattern from outside the system. Now that we've covered consistency, the next two concepts we need in order to state Gödel's theorems are decidability and completeness. First, decidability. A statement is decidable within a formal system if either it or its negation can be proved from the system's axioms using its rules of inference. For example, the Pythagorean theorem is a decidable statement within Euclidean geometry. By contrast, a statement is undecidable within a system if the system can express it, but neither the statement nor its negation can be proved from the axioms. For example, in a basic system of arithmetic called Robinson arithmetic, you can write the statement x plus y equals y plus x, but you can't prove it or disprove it from the axioms. However, you can prove particular cases like 5 plus 7 equals 7 plus 5. In a more powerful system like Peano arithmetic, the general rule x plus y equals y plus x is provable using a method called mathematical induction. So far, we've been talking about whether individual statements are decidable, but whole formal systems can also be called decidable or undecidable. A decidable system is one where there exists an algorithm that can tell, for any given statement expressible in the system, whether it's true or false. The algorithm might not be part of the system itself, and the proof that it works might come from outside the system, but as long as it exists, the system is decidable. If no such algorithm can possibly exist, the system is undecidable. For example, propositional logic is a decidable system. Propositional logic deals with single statements like P, Q, and their combinations using and, or, not, and implies. There's an algorithm, often implemented as truth tables, that can tell you whether any such statement is always true, a tautology, always false, a contradiction, or sometimes true and sometimes false, a contingency. By contrast, Peano arithmetic is undecidable. No algorithm exists that can determine in general whether every possible arithmetic statement is true or false. Closely related to decidability is the idea of completeness. A system is complete if every true statement expressible within it can also be proved within it. This is different from decidability. Completeness doesn't require a single algorithm that handles all cases. It just requires that each individual true statement has some proof inside the system. An example of a system that's complete but not decidable is first-order logic including equality, as long as it doesn't include function symbols. This system includes logical quantifiers like for all and there exists, along with predicates that describe properties of objects. On the flip side, a system can be decidable but not complete. That is, there might be an algorithm that can tell whether any statement is true or false, even though not every true statement can be proved within the system. These systems tend to be artificial or specially constructed, so I'll say no more about them here. The fourth concept we need in order to grasp Gödel's incompleteness theorems is something called arithmetization, as the term is used in mathematical logic. Arithmetization refers to a specific kind of encoding, a way of representing information using natural numbers. By natural numbers, I mean 0, 1, 2, 3, and so on. It's not hard to see that any precise and finite body of information, or any combinatorial process, can be encoded using natural numbers. Take, for example, a long book like Moby Dick. How could we encode the entire text of that book using nothing but numbers, or even a single number? Simple. First, we make a complete inventory of all the symbols that appear in the book. The 26 lowercase Roman letters, the 26 uppercase ones, the same set in italics, the 10 Arabic numerals, various punctuation marks, special characters like ampersands or dollar signs, even the spaces between words and the paragraph breaks. Suppose this adds up to around 300 distinct symbols. It's probably fewer, but let's just say 300. Then we assign each of these symbols a unique number, say a 4-digit number, using only the digits 0 through 9. We'll skip the first 999 numbers since those can't form true 4-digit numbers without a leading 0. Even with that constraint, we still have more than enough 4-digit numbers to assign a unique numerical tag to each symbol in our character set. Once that's done, we can encode the text of Moby Dick by replacing each symbol in the book in order with its assigned 4-digit number. The result is a long string of digits, but this string is itself just one gigantic number. And it's easy to decode. Just break the number into 4-digit chunks, look up each one in the symbol table, and reconstruct the original text. So far, this is just a way of encoding non-numerical data as a number. But for Gödel's purposes, arithmetization means something more. What makes it arithmetization in Gödel's technical sense is this. We're not encoding just any information. We're encoding a formal system. And we're doing it in such a way that its rules of syntax and inference also get translated into statements about natural numbers. Once we've done that, once we've encoded a formal system in arithmetic in this specific way, we've arithmetized it. To prove his incompleteness theorems, Gödel arithmetized a particular formal system, which he called System P. This system is a formalized system of arithmetic, meaning it was a formal version of the science of natural numbers. Certain definitions, statements, and proofs about natural numbers were formally representable within System P. We needn't worry about all the details of Gödel's arithmetization or about the precise definition of System P. It's built by combining the formal logic of a system called Principia Mathematica with the axioms of another system called Peano arithmetic. But taking a quick look at some simplified examples may help clarify what it meant for Gödel to arithmetize an entire formal system like System P, which in turn will help us understand why the method is so powerful. Let's do that in 4 steps. First, we'll see how Gödel coded the alphabet of symbols for System P. Second, how he coded any given string of symbols. Third, how he coded the axioms of System P. And fourth, how he coded the rules of syntax and inference for the system. In the process, we won't be sticking to the precise specifications of Gödel's actual System P. We'll use whatever specifications are most convenient for illustration. So let's start with how Gödel found a way to code the symbols of a formal system as numbers. Suppose our formal system uses just a small set of symbols, say lowercase and uppercase A through Z, the digit 0, some basic punctuation like parentheses, commas, and periods, plus a few mathematical symbols like plus signs and equal signs. For concreteness, let's say we're working with 128 distinct symbols. Now imagine assigning each of these symbols a unique number from 1 to 128. We can do that any way we like. For instance, we might assign the lowercase letters the numbers 1 through 26 in alphabetical order, then give the uppercase letters the numbers 27 through 52, then assign to the digit 0 the number 53. The punctuation marks and special symbols listed in some order of our choosing can be assigned the remaining numbers in sequence. We'll call those numbers the Gödel numbers of the symbols. This kind of mapping, from symbols to numbers, is called a coding. And since these numbers represent the basic elements of a formal system, its symbols, we call it a symbol coding. Gödel's actual symbol coding was more elaborate, since the formal language of System P is more complex than the alphabet I just described, but we can ignore those details. Any one-to-one mapping from a finite symbol set to the natural numbers will work just fine for understanding the basic idea. Next, let's see how Gödel could encode any finite string of symbols from his alphabet. Once we've assigned Gödel numbers to the individual symbols, we can use those to assign numbers to whole strings of symbols. But here a problem arises, and Gödel's solution is both clever and elegant. Suppose, for example, we want to assign a unique number to the string S0 blank space equals blank space SS0, such that the number represents just that string of symbols in that order and nothing else. In our Gödel numbering scheme, let's say the symbol capital S has the number 45, 0 has the number 53, a blank space is 68, and the equal sign is 54. That means the Gödel numbers for our string symbols in order are 45, 53, 68, 54, 68, 45, 45, 53. Now the question is, can we use these individual numbers to build a single unique number that represents the whole string? We might try the sort of thing we did with the text of Moby Dick. Just string the numbers together into a single big number. In this case, one with 16 digits, 4, 553, 685, 468, 454, 553. But now we hit the problem. This number doesn't unambiguously encode a single string because it can be broken up in multiple ways. Take the first 4 digits, 4553. Does that mean the 4 symbols numbered 4, 5, 5, and 3? Or does it mean 2 symbols, 45 and 53? Our encoding doesn't tell us, and that's no good. We need a way of assigning a number to a string that's unique, unambiguous, like a social security number. Gödel's solution? Use prime numbers. He took advantage of a beautiful mathematical fact, the unique factorization theorem, also called the fundamental theorem of arithmetic. It says that every positive integer greater than 1 can be expressed in exactly one way as a product of prime numbers, like 2, 3, 5, 7, 11, and so on, raised to various powers. Gödel used this fact to encode strings with perfect precision. Here's how. Take the first prime, 2, and raise it to the Gödel number of the first symbol. Then take the next prime, 3, and raise it to the Gödel number of the second symbol in the string. Then 5 to the third symbol, 7 to the fourth, and so on. So for our 8-symbol string, whose individual symbols have the Gödel numbers 45, 53, 68, 54, 68, 45, 45, 53, we construct a single number by multiplying powers of primes like this. 2 to the 45 times 3 to the 53 times 5 to the 68 times 7 to the 54 times 11 to the 68 times 13 to the 45 times 17 to the 45 times 19 to the 53. That number will be enormous, but that's okay because it's unambiguous. Thanks to unique factorization, there's only one way to break that number back down into its prime powers. If we were handed that big number, we could, in principle, factor it and see it has 8 prime factors, so the string is 8 symbols long. And the exponents on those primes tell us which symbols those are in order. So, no 2 strings will ever have the same Gödel number. Elegant, precise, and deeply clever. These giant numbers, built this way, are the Gödel numbers for strings of symbols. Gödel's actual encoding was more involved to ensure certain desirable properties like being primitive recursive, but this simplified look captures the key idea. Now that we've seen how to assign a unique Gödel number to any string of symbols in our formal system, it's easy to see how to assign Gödel numbers to the axioms of the system. Since System P is a formal system for arithmetic, a symbolic system designed to express the properties and truths about natural numbers, it must be able to express the axioms of that science too. That means that an axiom in System P is just a particular string of symbols. So, if the axioms can be written as strings of symbols in P's alphabet, and we already know how to assign a unique Gödel number to any such string, then we already know how to assign a Gödel number to each axiom of P. The same method works for whole proofs. A proof in the formal language of P is just a finite sequence of formulas, that is, a sequence of statements written in the symbols of the system. Suppose some proof contains 7 statements. To assign it a Gödel number, we do just what we did for individual symbol strings. We use powers of primes. Specifically, we take the first 7 consecutive primes, starting with 2, and raise each one to the Gödel number of the corresponding statement in the proof. So if the Gödel number of the 5th statement is g, then the 5th prime, which is 11, is raised to the power g, giving us the factor 11 raised to the power of g. We repeat this for all 7 statements, then multiply those 7 prime powers together. The result? is the Gödel number for the whole proof. The rules of syntax and inference are a different story. These rules govern how we can manipulate and transform symbolic expressions within the formal system to derive new theorems. But unlike the symbols or strings themselves, these rules aren't expressions within System P. They aren't symbol sequences. They're statements about how symbols may be combined and used. To represent these rules arithmetically, Gödel had to find a way to reflect them within the language of numbers. He did this by showing that the logical properties and relationships between symbolic expressions, things like is a well-formed formula, or is the result of applying this rule, or is a valid proof, could be mirrored by purely arithmetic relationships between the Gödel numbers that correspond to the symbolic expressions exhibiting these various logical properties. In other words, Gödel didn't just encode the static parts of the formal system, its symbols, axioms, and formulas. He also arithmetized the rules, the dynamic machinery that allows one formula to follow from others. He translated the meta-language, the language we use to talk about the system, into the object language of arithmetic itself. That move was the key to everything that followed. It made possible the construction of self-referential statements, formulas that, in a sense, talk about themselves, especially about their own provability. But we're getting ahead of ourselves. So far, we've seen how Gödel translated the symbols and axioms into arithmetic by assigning each a number, its Gödel number. But when it came to translating rules, he couldn't just assign them numbers in the same way, because rules are about symbols and strings, not themselves strings of symbols. So instead, Gödel found a way to represent rules indirectly, by identifying one-to-one correspondences between those rules and certain relationships between Gödel numbers. That's how he brought even the rules of inference into the world of arithmetic. So, when it came to the system's rules of syntax and rules of inference, Gödel didn't encode these simply as numbers. Instead, he encoded them as statements about numbers. Take this basic rule from piano arithmetic. If t is a term, then s of t is a term. Note that it's not just a string of symbols from within the system, but it's a statement about them. Let's see how to arithmetize that. That is, how to find a statement about natural numbers that mirrors what the original rule says. First, we need to understand what term means here. A term is any syntactic expression in the formal system that represents a natural number. So for example, 0 is a term, since it denotes a number. But so is S0, which means the successor of 0, which is 1. And so is SS0, namely 2, and SSS0, namely 3, and so on. Now in general, natural numbers in piano arithmetic can also be represented as sums, products, or variables, like x, or S0 plus SSS0, which equals 4. But for now, just to keep things simple, let's artificially restrict our attention to terms made only of the symbols s and 0, nothing else. No addition, no variables. Let's call these kinds of terms successor expressions. Then our rule becomes, if t is a successor expression, then s of t is also a successor expression. Can we arithmetize that particular rule? That is, can we find a truth about natural numbers that corresponds exactly to this statement about successor expressions? We can. Here's how. Let's list a few successor expressions along with their Gödel numbers. So we're pairing 0 with 2 to the 53rd, S0 with 2 to the 45th times 3 to the 53rd, SS0 with 2 to the 45th times 3 to the 45th times 5 to the 53rd, and so on. Notice the pattern. Each Gödel number is formed by multiplying together a sequence of primes, starting from 2. The last prime in the product is raised to the power 53, and all the earlier primes, if any, are raised to 45. Let's give a name to numbers that follow this pattern. We'll call them successor numbers. Now we can rewrite our rule of syntax this way. If the Gödel number of an expression is a successor number, then the number we get, if we change the 53 in its last exponent to 45 and tack onto the product the next prime number raised to 53, is also a successor number. That's a statement purely about numbers, and it mirrors exactly the logic of our syntactic rule about expressions. Now this is not exactly how Gödel did it. He wasn't just dealing with successor expressions, he had to encode the full general rule, if t is a term, then s of t is a term. And not just that, he had to encode all the syntax rules and all the rules of inference in terms of arithmetic relationships. But this simplified example gives us a feel for how arithmetization works. Gödel found ways to translate everything about System P, its symbols, formulas, axioms, syntax, and inference rules, into statements about natural numbers. He represented the whole structure of the formal system within arithmetic itself. The ingenious thing about this method, and the reason Gödel's proof works, is that it lets us translate statements and arguments about the system P itself into statements and arguments about natural numbers. For example, the metamathematical statement S0 is a successor expression becomes the arithmetical statement 2 to the 45th times 3 to the 53rd is a successor number. Likewise, Gödel was able to take a meta-level claim like, this sequence of formulas is a proof of that formula in system P, and translate it into a statement about numbers, specifically the Gödel numbers of those formulas. He also built a formula, an actual arithmetic predicate, often written as prov xy. Here's what that formula means. Y stands for the Gödel number of some formula in system P. X stands for the Gödel number of a sequence of formulas, what we might call a proof candidate. Prov xy is true of x in relation to y if and only if that sequence x really is a valid proof of the formula y under the rules of system P. In short, prov xy expresses x proves y, but entirely in the language of arithmetic. A quick caveat, while prov xy expresses x is a proof of y, the statement used in Gödel's theorem is more like there exists an x such that prov xj holds of x in relation to j, which maps to saying there's a sequence of statements with Gödel number x, which constitutes a valid proof of the statement with Gödel number j. In this way, Gödel arithmetized the concept of provability itself. With this technique, he gave us a way to translate metamathematical questions about proofs, formulas, and validity into questions about numbers. And that's the heart of arithmetization. Okay. Now we come to the final prerequisite for understanding just what Gödel's incompleteness theorems say. This prerequisite is the concept of a formal system being sufficiently rich for Gödel's theorems to apply to it. We need that concept to appreciate Gödel's strategy in proving his first incompleteness theorem. At the heart of that strategy was showing that within the language of the formal system P, the system he was working with, it's possible to construct a certain fascinating self-referential statement, one that effectively asserts that it itself is not provable within system P. Recall that Gödel had successfully arithmetized P to the point where statements about what is and isn't provable in P could be translated into corresponding statements about numbers and numerical functions. In particular, he constructed a predicate expressing relations of numbers, prov xy, such that if you input a number x, which is the Gödel number of some sequence of formulas in P, and a number y, which is the Gödel number of some one formula, then the numerical relationship prov xy holds of x in relation to y if and only if the sequence of formulas coded by x constitutes a valid proof within P of the formula represented by y. Using this arithmetization of provability, Gödel devised a method of showing that it's possible to construct a specific sentence, let's call it G, which is a well-formed formula consisting in symbols from the language of P, whose Gödel number we may call J, which sentence effectively says, if we express its equivalent in English and not in the symbols of P, that for all x, prov xj is false. But the actual sentence G itself is written in the language of P and says there is no number x such that prov xj holds of x in relation to j. Here x is a free variable, and we already said j is the Gödel number of this very sentence G. Thanks to the way prov xj formalizes the notion of provability within P, the statement effectively says of itself, this sentence is not provable in system P. This intriguing self-referential sentence is called the Gödel sentence of system P. We can see just what it's saying about itself if we recall that the numerical provability predicate, prov xj, is Gödel's way of encoding or arithmetizing provability. The arithmetical predicate, prov xj, expresses a numerical relationship between x and j that holds if and only if the series of statements in P, for which x is the Gödel number, constitutes a valid proof within P of the statement whose Gödel number is j. So when G says that this numerical relationship does not hold for any value of x, it's effectively saying that the statement whose Gödel number is j has no valid proof in system P. But the statement whose Gödel number is j is none other than G itself. So G is telling us that it itself is not provable in system P. Also, the provability predicate prov xj will be false for all x, and its negation, which is the sentence G, will be true if and only if G is unprovable in system P. That's key. G is true if and only if it is not provable in system P. I never cease to be amazed both by Gödel's ingenuity in coming up with this and by the fact that this was possible to come up with at all. By the fact that it's possible to get a sentence of a formal system to say something about its own unprovability in that system. In a moment, we'll see how Gödel used the Gödel sentence G to prove his first incompleteness theorem. But before we do, we need to use it to define what we mean by a system being sufficiently rich or sufficiently expressive. Since Gödel's proof relies on the possibility of forming a Gödel sentence G, his theorem doesn't apply and can't apply to any formal system whose language isn't sophisticated enough to construct such a sentence. Not every formal system can be made to talk about itself the way the Gödel sentence makes system P talk about itself. And that's because Gödel's numerical provability predicate, prov xj, which is part of the Gödel sentence, doesn't just depend on the natural numbers in basic arithmetic. It also depends on the system being able to express things like logical relationships, quantifiers, and recursively defined relations. That last idea, recursion, is best seen by example. A classic example is the definition of factorials using recursion. Here's how it works. First, we have a base case defining 0 factorial as being equal to 1. Base case 0 factorial equals 1. Recursive case for n greater than 0, n factorial is equal to n times n minus 1 factorial. There's our pattern. This tells us how to compute the factorial of any positive integer n, though it might not look like it at first. Suppose we want to compute 4 factorial. Then by the recursive case in our definition, we have 4 factorial equals 4 times 4 minus 1 factorial equals 4 times 3 factorial. And 3 factorial is equal to 3 times 3 minus 1 factorial, which is equal to 3 times 2 factorial. And 2 factorial is equal to 2 times 2 minus 1 factorial, which equals 2 times 1 factorial. And 1 factorial is equal to 1 times 1 minus 1 factorial, which is equal to 1 times 0 factorial, which is 1. Once we reach 0 factorial, we've come to the base case in our definition, which we've defined as being equal to 1, so plugging that into the recursive expression for 1 factorial, we can now fully compute 1 factorial, and then plugging the known value of 1 factorial into the recursive expression for 2 factorial, we can compute its value, and so on all the way up to 4 factorial. Now that may seem like a roundabout way to define factorials, but recursion allows us to define extremely sophisticated functions, and Gödel needed such functions in order to construct his numerical provability predicate. So, a formal system F, to speak more generally than just of Gödel's system P, is considered sufficiently rich or sufficiently expressive or arithmetically adequate to construct a Gödel sentence if it satisfies the following conditions. It can represent the natural numbers and basic arithmetical operations like addition and multiplication. It includes basic numerical relations like less than and equal to. It's based on first-order logic with standard logical connectives and quantifiers like and, or, not, implies, for all, there exists. It can represent all primitive recursive functions and relations, or at least those necessary to simulate basic computation. For example, it can define the factorial function recursively. And it can arithmetize its own syntax, that is, encode statements, proofs, and the notion of provability using numbers. Only when a system has all of these capabilities is it rich enough to write a Gödel sentence. If it's missing even one of these crucial ingredients, it won't be sufficiently expressive to carry out Gödel's construction. For example, Pressburger arithmetic, the theory of addition over the natural numbers without multiplication, is not sufficiently rich. Even though it can express a lot, it doesn't have enough power to construct a Gödel sentence. Similarly, Skolem arithmetic, which focuses on multiplication but without addition, is also not expressive enough for Gödel's purposes. Well, that's it for prerequisite concepts. We now come to part 2 of the video, since we're ready to state Gödel's incompleteness theorems. His first incompleteness theorem can be stated like this. Every consistent, computably axiomatizable, and sufficiently expressive formal system of arithmetic contains statements that are true about natural numbers, true in the standard model of arithmetic, but not provable within the system. Let's go through that statement term by term. Consistent means the system doesn't prove both a statement and its negation. That was the second sense we talked about earlier, right after the more general everyday meaning of consistent. Now, Gödel's original proof assumed the slightly stronger condition called omega consistency, but it was later shown by J. Barclay Rosser that the theorem still holds, assuming only simple consistency. Computably axiomatizable means there's an algorithm, a mechanical procedure, that can determine whether a given formula belongs to the system's set of axioms. In other words, the axioms are recursively enumerable. Sufficiently expressive or sufficiently rich, we covered a moment ago. It means the system can express enough arithmetic to express certain properties of natural numbers and basic functions. Formal system we've defined already, so that should be old hat by now. But a formal system of arithmetic in particular just means a formal system that captures the logical structure of some deductive body of knowledge about the natural numbers. There are also formal systems for other domains like geometry, physics, and so on. And the rest should now be clear. Basically, the first incompleteness theorem says that if a formal system of arithmetic has computably listable axioms and is sufficiently expressive, then it cannot be both consistent and complete. It has to choose. If it's complete, that is, if every statement expressible in the system can be derived from its axioms, then the system must be inconsistent and able to derive contradictions. But if it's consistent, then it must be incomplete. There will be true statements the system can express but cannot prove. That's an astonishing result, and the world still hasn't finished absorbing all its implications. But let's take a moment to think through a rough sketch of Gödel's argument. Without diving into the technical details of System P specifically or Gödel's arithmetization of it, we can still get the gist of his proof. Let's do that now. Suppose we're given a formal system of arithmetic, which we'll call F, and suppose the following things are true of F. There's a way to list off its axioms such that none will be missed if we carry on the listing method long enough. F is consistent. It doesn't prove both a statement and its negation. And F is sufficiently rich to formulate a Gödel sentence G. Good. To establish the theorem, all we need to do is show that there exists a true sentence in F that F cannot prove. And what we'll show specifically is that the Gödel sentence G for system F is just such a sentence. It's a truth about natural numbers expressible in F, but not provable within F. To see that, we start by supposing the contrary, that G is provable within F. If that assumption leads us into a contradiction, then G must not be provable. And since G is constructed to say, in effect, G is not provable in F, this means that showing G is not provable in F would at the same time prove that G is true. So let's try to suppose G is provable in F. That means there exists some sequence of formulas within F that constitutes a valid proof of G. Let's call the Gödel number of that proof sequence K. Because K is the Gödel number of a valid proof of G, whose Gödel number is J, the arithmetical formula prov Kj must be true in the standard model of arithmetic. That is, it must say something true about the natural numbers K and J. This is because the prov xy formula was designed by Gödel to be true in the arithmetic of natural numbers precisely when x codes a valid proof of the formula coded by y. So given that K is the Gödel number of a proof of G, it follows from Gödel's arithmetization that prov Kj is a true arithmetical statement. Now, since F is sufficiently rich to represent its own syntax and proofs, it can also express and prove specific facts about Gödel numbers, facts that correspond to truths about its own proofs. Think of it this way. If you have a valid proof in F and have assigned numbers to all the symbols in it, then F, if it's powerful enough, should be able to recognize and prove that this sequence of numbers corresponds to a valid derivation of a particular conclusion. And prov Kj is just such a statement. It effectively says that the number K encodes a valid proof in F of the formula whose Gödel number is J. Therefore, not only is the arithmetical statement prov Kj true, but system F must be able to prove it, since the statement is both true and within F's expressive power. The fact that a formal system like F can prove a specific instance like prov Kj implies that the system can also prove a general statement, like there exists a number x such that prov xj is true. This is similar to how if the system can prove that 2 times 3 equals 6, then it can also prove there exists a y such that 2 times y equals 6, because the specific case, y equals 3, confirms the general existential claim. We're almost done. We've now shown that if G is provable in F, then F can also prove there exists a number x such that prov xj is true. But let's now recall what G actually says. In plain English, G says, for all x, prov xj is false. That is, there is no natural number x that encodes a valid proof in F of the formula with Gödel number j. So if G is true, then there does not exist a number x such that prov xj is true. And since F is consistent and supposedly proves G, therefore G is true. So if F is consistent and proves G, then there does not exist a number x such that prov xj is true. So a moment ago, we showed that if F proves G, then there does exist a number x such that prov xj is true. And now we've shown that if F proves G, then there does not exist a number x such that prov xj is true. In other words, we've shown that if G is provable in F, then F would prove both that there is and that there isn't a natural number x for which prov xj is a truth about the natural numbers x and j. In other words, if G is provable, then F would be able to prove contradictory statements. But we're given that F is consistent, meaning it cannot prove contradictions. So our initial assumption that G is provable must be false. Therefore, G is not provable within F. And since G says G is not provable in F, and we've just shown that G is indeed unprovable in F, G is actually true. So we found a sentence, G, that's true but not provable within F. And therefore, every consistent, computably axiomatizable, and sufficiently expressive formal system of arithmetic contains statements that are true about natural numbers but not provable within the system. And that concludes our sketch of the argument. We've now seen Gödel's first incompleteness theorem, which says that any consistent, computably axiomatizable, sufficiently expressive formal system of arithmetic must be incomplete. There will be true statements within it that it cannot prove. But Gödel didn't stop there. Just a few pages later, in his 1931 paper, he delivered a second incompleteness theorem, which says something even more unsettling. Such a system cannot prove its own consistency. Well, let's unpack that and work through a high-level sketch of the argument, just as we did with the first theorem. First, let's be precise about what this second theorem says. Suppose we have a formal system of arithmetic, again call it F, which satisfies all three key properties. F is computably axiomatizable, its axioms can be listed out by an algorithm. F is consistent, it doesn't prove contradictions. F is sufficiently expressive, it can represent basic facts about arithmetic and its own proofs. Well then, Gödel's second incompleteness theorem says F cannot prove a sentence that expresses F is consistent. And this holds even though F is consistent. So even if everything in F is working perfectly, it still won't be able to demonstrate within itself that it's consistent. So how does the proof go? Well, here's the basic idea, again in informal but conceptually accurate steps. Start with the Gödel sentence G, constructed within a formal system F, such as Peano arithmetic. This sentence is carefully designed to say of itself, G is not provable in F. So if F is consistent, then G must be true about natural numbers but unprovable within F. This is the content of Gödel's first incompleteness theorem. From this we know, if F is consistent, then G is not provable. And G asserts that it's not provable, so if F is consistent, G must be true. But then the negation of G, not G, must be false. Therefore, if F could prove not G, it would be proving a falsehood. So if F proves not G, it must be inconsistent. Putting that last statement in contrapositive form, if F is consistent, it cannot prove not G. This implication, if F is consistent, then not G is not provable, is logically equivalent to a weak form of F's consistency. Gödel's key insight was to arithmetize this idea. He represented the statement F is consistent as a formula inside F itself called conf. This formula roughly says there is no number x that encodes a proof of a contradiction in F. Or more concretely, there's no number x that encodes a proof of 0 equals 1. Now comes the critical step. Gödel showed that if F could prove conf, that is, prove its own consistency, then it could also prove G, its own Gödel sentence. Why is that? Because from the structure of G we know if F is consistent, then G is not provable. And from the structure of G we also know if F proves conf, then it proves that F is consistent. So if f is strong enough to reason about its own proofs, as it is, then it can combine these two facts and derive g itself. That is, it can prove con f, hence its own consistency, hence prove the unprovability of g, which of course is the same as to prove g itself, since g just asserts the unprovability of g. So, if f proves con f, then it proves g. But from the first incompleteness theorem, we know that if f is consistent, then it does not prove g. Therefore, if f is consistent, it cannot prove con f. That is, it cannot prove its own consistency. If it did, it would also prove g, which it cannot do. Well, this is Gödel's second incompleteness theorem. A consistent formal system f that's capable of expressing arithmetic cannot prove its own consistency. Well, there you have a brief breakdown of the main moves in Gödel's proof of his second incompleteness theorem. To make the argument fully rigorous, we would need to show that system f can actually encode the reasoning of the first theorem within itself. That is, we would have to formalize and arithmetize the entire structure of the first incompleteness proof inside f. But our informal and non-rigorous look at the basic strategy is enough to grasp the core insight. Incidentally, the original proofs that Gödel gave for his theorems are fairly difficult to learn, but much simpler approaches have been developed since then, some of them coming from computer science, using tools like Turing machines and formal logic tailored for computation. So, if you're interested in seeing fully worked out proofs of Gödel's theorems, you might want to explore some of those computer science-based presentations rather than start with Gödel's original work on formally undecidable propositions. Now that we've gone through what Gödel's theorems actually say, we come to part 3 of this video and consider how those theorems have been used in arguing for the conclusion that artificial intelligence cannot truly think or understand. We owe such arguments to the British philosopher John Randolph Lucas, who published them in a 1961 article titled Minds, Machines, and Gödel, published in the journal Philosophy. Nearly 3 decades later, the English mathematician, physicist, and philosopher Roger Penrose picked up and extended Lucas's line of thought in The Emperor's New Mind in 1989. More recently, physicist Stephen Barr advanced a similar argument in his book Modern Physics and Ancient Faith, 2003. From Lucas's article, it's possible to extract 2 distinct arguments, one corresponding to each of Gödel's 2 incompleteness theorems. Lucas wrote, Gödel's first incompleteness theorem must apply to cybernetical machines because it's of the essence of being a machine that it should be a concrete instantiation of a formal system. It follows that for any given machine which is consistent and capable of doing simple arithmetic, there's a formula which it's incapable of producing as being true. That is, the formula is unprovable in the system, but which we can see to be true. It follows that no machine can be a complete or adequate model of the mind, that minds are essentially different from machines. Lucas appears to be reasoning as follows. A true mind is capable of recognizing the truth of a Gödel sentence constructed within any given consistent formal system that's rich enough to express arithmetic. But a machine, if it operates by executing a formal system, as all programs do, and if that system is consistent and rich enough to produce a Gödel sentence, will be unable to recognize the truth of that sentence. Therefore, a true mind cannot be the same thing as a machine running such a formal system. Since this result is a universal negative, it can be logically converted. No machine, simply by implementing a formal system of that kind, can be or have a true mind. With that slight clarification, we can restate the argument like this. Premise 1. Every true mind can determine the truth of a given Gödel sentence, one written within a given consistent formal system rich enough to express arithmetic. Premise 2, no machine that merely implements a formal system can determine the truth of a given Gödel sentence, since it cannot prove or disprove the Gödel sentence corresponding to the program it's running. Therefore, no such machine is a true mind. Premise 1 is based on the idea that mathematicians can see, in a general and principled way, that the Gödel sentence associated with any such formal system must be true. They may not be able to explicitly write out the sentence for a particular system, but they understand, thanks to Gödel's first incompleteness theorem, that it exists and that it must be true. Premise 2 simply applies that theorem to a machine running a program or algorithm. A programming language, if it's Turing complete and has facilities for manipulating representations of its own code, can have a formal system built inside it that's rich enough to support the writing of a Gödel sentence. Interactive theorem provers or proof assistants like Lean and Isabelle HOL are examples. Moreover, the mathematical foundations of machine learning, such as linear algebra and calculus, are implemented within AI systems, including large language models, by using formal systems, and the algorithms they run operate within those systems as well. So AI systems either are formal systems themselves, or else heavily rely on formal systems, or at the very least rest on mathematical foundations that can be formalized. These systems are also presumed to be consistent, since they're built on the rules and objects of arithmetic or number theory. The very operations performed by computers are grounded in formal arithmetical systems. Furthermore, the logical and mathematical foundations of computer science, including those underpinning large language models, are rich enough to express basic arithmetic. They're Turing complete, meaning they can compute any computable function, and that entails being able to represent any formal system to which Gödel's incompleteness theorems apply. It follows, then, that there will always be true statements about the underlying computational systems that cannot be proven within it. Later on in his article, Lucas puts forward a second argument, this time grounded in Gödel's second incompleteness theorem. In summary, the argument runs like this. Every true mind, such as a human mind, can recognize its own consistency, but no machine operating via a consistent, rich formal system can do the same for itself, and therefore no true mind is such a machine. As with the earlier argument, this universal negative can be logically converted so that we can argue like this. Every true mind can determine its own consistency. No machine that operates purely by implementing a consistent and sufficiently rich formal system can determine its own consistency. Therefore, no such machine is a true mind. This conclusion leads directly to a corollary. No AI system can be or possess a real mind, since any such system would necessarily fall under the category of machines described in this argument. Stanley Yockey, in his book Mind, Brain, and Computers, endorsed and further developed this same line of reasoning. Lucas defends premise 1 by appealing to our ordinary experience of being minds. He acknowledges that human beings can be inconsistent in the everyday sense. They make mistakes, hold conflicting beliefs, or even lose their minds entirely, which may lead them to stop caring about consistency. Still, most people who retain the use of their minds generally strive to be consistent, or are capable of doing so, and will try to eliminate contradictions in their thinking when they notice them. Some people, like Meno, a figure in Plato's dialogues, may not care whether their beliefs hang together logically. But others, like Socrates, clearly do care. So human beings, as Lucas sees it, possess minds that are at least capable of examining themselves for internal consistency, even if not all of them choose to exercise that capacity. Premise 2, again, follows directly from Gödel's second incompleteness theorem, applied to any machine running a program that qualifies as a formal system to which the theorem applies. We come now to part 4 of this video, and consider some objections that have been raised against these arguments. Even before Lucas published his famous article, Alan Turing had already anticipated and rejected this type of reasoning based on Gödel's first incompleteness theorem. Writing in 1950, Turing addressed the idea that the human mind can see the truth of a Gödel sentence that a given machine cannot prove. He remarked, "Our superiority can only be felt on such an occasion in relation to the one machine over which we've scored our petty triumph. There would be no question of triumphing simultaneously over all machines." In other words, while we might recognize the truth of a Gödel sentence that some particular machine, call it machine A, cannot prove, we can't claim to see the truth of a Gödel sentence that's unprovable by any machine. It's always possible to construct a new machine, machine B, built to operate on a different system that can prove what A could not. Besides, there are things our machines can prove whose truth we cannot see, because the proofs are too long and complex for our minds. Well, to this, Lucas responds, persuasively I think, that Turing's reply shifts attention away from the core issue. The real question is not whether a machine can outperform a mind in some contest of problem solving, but whether a mind and a machine are the same kind of thing. Lucas's point isn't about superiority, but non-identity. He also accuses Turing of mischaracterizing just what it is that the human mind can triumph over. Do we really triumph over just one machine, or over all of them? True, says Lucas, the machine can do many things that a human mind cannot do. But if there is of necessity something that the machine cannot do, though the mind can, then, however trivial the matter is, we cannot equate the two, and cannot hope ever to have a mechanical model that will adequately represent the mind. Nor does it signify, he means it doesn't matter, that it's only an individual machine we have triumphed over. For the triumph is not over only an individual machine, but over any individual machine that anybody cares to specify. Lucas is drawing a subtle but crucial distinction between an individual instance and any individual instance. Think of Euclid's first proposition. It doesn't just show us how to construct an equilateral triangle on a specific finite line, it shows how to do so on any such line. Even though we can only perform the construction in one case at a time, we know in advance that the procedure will work for every new line we might try. Likewise, Gödel's first incompleteness theorem provides a method for constructing, for any consistent formal system capable of expressing arithmetic, a Gödel sentence that's true but unprovable within that system. Thanks to the theorem, we don't need to carry out the construction for each system in practice. We already know that the method works in all such cases. In The Emperor's New Mind, Roger Penrose responds to a related objection. Someone might argue that for a very complex system, we might be unable to actually construct the Gödel sentence G. And if we can't even construct it, how can we claim to know it's true? But that objection misses the deeper point. Gödel's theorem doesn't just provide a method for generating G in any given system, it also assures us in general that such a G will exist for every consistent, sufficiently expressive formal system, and moreover assures us that G is true. Even if G is too complex to construct in practice, the theorem tells us it's there and it's true. Again, it's like Euclid's triangle. The procedure guarantees that the triangle can be constructed in every case, even if we never do it. We don't need to actually perform the construction each time to know, in principle, that it works universally. Another objection targets the premise that every true mind can determine the truth of its Gödel sentence. Turing expressed skepticism about this in his 1950 paper, and Douglas Hofstadter raises similar doubts in Gödel, Escher, Bach. After all, not every human being can follow Gödel's proof, let alone understand what it says. So how can this premise be true? That not everyone can follow Gödel's reasoning or understand what his theorems say is undeniable. But the premise isn't about individual human capabilities, it's about the kind of power the human mind has, the ability to grasp universals. Not every mind can grasp every universal, but all human minds can grasp some, and the species as a whole can grasp many, including, crucially, the universal form of Gödel's theorem. The human mind, at least as a kind of being, is capable of seeing that for any formal system to which the theorem applies, the corresponding Gödel sentence is true but unprovable within that system. By contrast, a machine working within a formal system doesn't grasp the meaning of universals, it merely manipulates symbols. That's precisely why it can't grasp the truth of its own Gödel sentence. Once we begin formulating the argument that way, however, we seem to be drifting away from Lucas's argument and closer to one like Searle's. This objection may deserve further attention, so I'll return to it when offering my final reflections. So much for objections to premise 1, which holds that the mind can see what the machine cannot. Other critics focus instead on whether the conclusion of the argument actually applies to AI. Even if Gödel's theorems show that no machine operating purely on a formal system is a mind, does it follow that no AI system is a mind? Perhaps it's too reductive to think of an AI as merely a formal system in operation. Hofstadter suggests this in Gödel, Escher, Bach, and Turing hinted at it as well. An AI might be built on a formal system F, but it might then use F to construct and operate higher-level systems with new properties. Today, it even appears possible for some AIs to revise or adapt such systems in response to input, to learn. So maybe it's too simplistic to describe an AI as a static embodiment of some fixed formal system F. One reply to that objection is that most AIs today do not revise or generate entirely new formal systems. They aren't formal theorem-proving systems modifying their own axioms or inference rules. Even systems that change their behavior, such as LLMs with memory or online learning agents, are still governed by higher-level meta-algorithms. That is, some overarching program, written by human beings, still constrains what they can do. And even if an AI did revise its formal system, the process by which it did so would itself need to be formally specified, meaning we could just move up a level and consider the whole metasystem to which Gödel's theorem would apply again. Lucas himself replies to this kind of objection, urged by Hofstadter and others, by pointing out that if a non-mechanical mind somehow emerges from mechanical parts, then the mechanist has conceded Lucas's point. The debate isn't about how minds arise, but about how they function. For the mechanist thesis to hold, a model of the mind must operate mechanistically, meaning its behavior can be explained purely in terms of its parts, each governed by deterministic or randomly determined rules. If that no longer holds, then by definition we're no longer dealing with a machine in the relevant sense. What's at stake in the mechanist debate, says Lucas, is not how minds are or might be brought into being, but how they operate. If the mechanist produces a machine which is so complicated that mechanistic explanation ceases to hold good of it, then it's no longer a machine for the purposes of our discussion, no matter how it was constructed. Lucas's point does not seem to be that a real mind might emerge from a machine, but only that if it did, then it would no longer be fully mechanistic. Entertaining the idea that a mind might emerge from a machine should be tempered by John Searle's challenge. If we're going to claim that machines can truly think, and not merely simulate thought, then we need compelling reasons, since cognition is the only biological function we seem prepared to attribute to machines in this way. Simply asking whether a mind might emerge isn't enough. One must show why we should believe it actually can or does. There's one more objection to consider, this time to premise 2, which claims that no machine operating on a consistent, rich enough formal system can prove its corresponding Gödel sentence. The objection goes like this. We don't possess any one-size-fits-all test for telling whether a given system is consistent. And in fact, we often don't know whether a formal system is consistent. So how can we be sure Gödel's theorem even applies to it? If we don't know whether the system is consistent, we can't know whether the Gödel sentence is true, and thus we're in the same position as the machine. Lucas addresses this. He acknowledges that some systems might be inconsistent, but argues that if so, they'll be utterly irrational and thus very poor models of the mind. But one might reasonably question this. Today's large language models, for example, are occasionally inconsistent. You can catch them contradicting themselves and sometimes even get them to admit it. That inconsistency probably stems, at least in part, from contradictions in their training data. I once pressed a popular LLM on this very point. I asked whether contradictions in its training data might explain why it sometimes contradicts itself. It initially said no. The real causes had to do with the complexity of language and imperfections in the data, such as biases, inaccuracies, and incomplete information. So I asked, if your training data can contain biases, inaccuracies, or incomplete information, then can't it also contain contradictions? And couldn't that be part of the reason why you contradict yourself? To this it replied, you've hit on a very important point. Yes, you're absolutely correct. If my training data contains biases, inaccuracies, and incomplete information, it can also contain contradictions. It then went on to explain why in some detail. So yes, the LLM was inconsistent, but far from utterly irrational, it's a remarkably useful tool. Lucas himself couldn't conceive of a mechanism that introduced inconsistency without also introducing complete irrationality. But absent a proof that this must be the case, we're left in doubt. And given how many of today's AI systems do exhibit some inconsistency without becoming useless, it's worth asking whether Lucas's assumption holds of our new systems. Perhaps there are inconsistent systems that remain largely rational and highly effective, and perhaps Gödel's theorems, which apply only to consistent systems, don't apply to them at all. Having seen some of the objections to the arguments based on Gödel's first theorem, we move on to part 5 of this video and take a look at objections to the Lucas-inspired argument based on the second theorem. That argument went like this. Premise 1, every true mind can determine its own consistency. Premise 2, no machine that operates purely by implementing a consistent and sufficiently rich formal system can determine its own consistency. Therefore, no such machine is a true mind. As in the case of the first argument, some would challenge the applicability of the conclusion to AI systems such as state-of-the-art LLMs. Is it fair to say that an AI system is such a machine, that it operates purely by implementing a formal system of the sort described? Or could it be that something other than that emerges when there are enough formal systems working in concert and at different levels? But most of criticism focuses on the first premise. Can we really know the consistency of our own minds? Our thought can operate for a long time on a set of principles we believe to be true and therefore consistent, only to discover later that some of those principles contained implicit contradictions. Naive set theory is an example of that, one that Lucas himself mentions in his article. He says that at least we know we can resolve to be consistent, and to root out contradiction whenever it rears its ugly head. But one wonders, why can't an AI system be made to operate in much the same way? Lucas points out that we can in many cases know the truth in a way that's neither a formal proof nor formalizable. Penrose, too, argues that even our mathematical thinking is non-algorithmic. Our direct experience of reality, for example, impresses upon us all sorts of universal truths that we simply know and do not prove at all, nor do we need to prove them, since they're instead evident in themselves, and they're the things in light of which we prove other things. At least these truths, those primary first principles, we know to be consistent, since they're all true, and true things are consistent with true things. Among those primary truths are the truths of our arithmetic, our basic number theory. If any of those were wrong, all of math and science would have to go with them. But we know that they're true. Statements such as 3 is an odd number, or a plus b equals b plus a, and the like, are either self-evidently true or else easily inferred from self-evident truths, and our original and natural certainty about them does not come from formal proofs provided by mathematical logic. Okay, so we've now looked at Gödel's incompleteness theorems and at two arguments based on them that aim to show AI systems cannot truly think and understand. Or equivalently, that whatever can truly think and understand cannot be a machine implementing a formal system to which Gödel's theorems apply. We've also considered some major criticisms of those arguments, along with Lucas's replies. Now I'll offer my own brief evaluation. To my mind, the most serious criticism of both arguments is that Gödel's theorems are specifically about formal systems, yet it's not clear that AI systems, especially large language models, actually are formal systems. A formal system is defined by a fixed set of axioms and inference rules, but LLMs don't work that way. They operate on patterns and probabilities, not on axioms and deduction. They aren't built for logical consistency, they're optimized for statistical accuracy. It's true that the machinery behind them depends on formal systems, as we've seen, but the whole LLM might not rightly be regarded as a formal system any more than a novel is rightly regarded as a sentence or a sentence as a word. And just as a sentence isn't subject to the limitations of a word, and a novel isn't subject to the limitations of a sentence, maybe an LLM isn't bound by the limitations of any single formal system it's built upon? For example, even if the underlying formal systems are consistent, the LLM itself clearly generates inconsistent outputs at times. So while Gödel's theorems might apply, it doesn't seem straightforward, and they might not apply at all. The second major criticism is that we can't know Gödel's theorems apply to a system unless we already know that the system is consistent, and we have no general way of establishing that for an arbitrary AI. Lucas's claim that any inconsistent system would be utterly irrational and therefore couldn't be a true mind or even a plausible model of one is perhaps compelling in the case of the more traditional systems that he would have had in mind. But now his assertion seems rooted more in his very understandable difficulty imagining a useful system that yields inconsistent results. And yet that's exactly what today's LLMs appear to be. So here too, it's hard to be sure Gödel's theorems apply in the relevant way. If those two criticisms can be adequately answered, then I think the arguments of Lucas and others would be about as strong as one could reasonably hope. But if not, then they don't seem as decisive or far-reaching as they first appear. Instead, they may apply only to a narrower class of machines, those that clearly and simply implement formal systems we already know to be consistent. Well, that's it for this video. In the next one, we'll begin looking at arguments that can be constructed on principles drawn from Aquinas and Aristotle. See you there.